and we'll keep drifting, floating together through the mysteries. 100 Cosmology Mysteries, looping softly, endlessly, through the night. Tonight we'll drift through the silent collision of galaxies millions of years from now, the ghost-like particles of dark matter passing through your palms as you sleep, and the final, lonely spark of the last star in the universe. There's nothing you need to do now. Just let your body sink, heavier, heavier. Feel the mattress holding you, every muscle softening, your heartbeat slowing, thump, thump, matching the rhythm of space itself. Shoulders melting down, jaw releasing, each breath pulling you deeper, deeper into the calm, the quiet, the dark. If this helps you rest, tap subscribe, comment, and hit like so others can find this calm too, but only if your eyes are still open. Otherwise, just drift. Now, let's drift into cosmology. Imagine, if you can, a point, smaller than the smallest thing you've ever seen, smaller than an atom, smaller than anything, containing everything, all of space, all of time, all of matter, compressed into a singularity, a place where the laws of physics fold in on themselves, where temperature becomes infinite, where density becomes infinite. This was the Big Bang singularity, 13.8 billion years ago. Not an explosion in space, but an expansion of space itself. Space, blooming, unfurling, like a flower opening in the dark. Your breath, slow, steady, matching the rhythm of cosmic expansion. And in that first, incomprehensibly small fraction of a second, the Planck epoch, time itself existed in quantum foam, a roiling sea of possibility where gravity and quantum mechanics danced together, where space-time itself flickered in and out of existence. 10 to the power of minus 43 seconds, the shortest meaningful measure of time, the universe, smaller than a proton, hotter than thought itself. Feel your body sinking, heavier into the mattress as we drift back through time. Then came the grand unification epoch, when 3 of the 4 fundamental forces were still one: electromagnetism, the weak nuclear force, the strong nuclear force, unified, indistinguishable, a universe governed by a symmetry we'll never see again, lasting only until 10 to the minus 34 seconds before that symmetry shattered, your eyelids growing heavier, heavier. The electroweak epoch followed, when electromagnetism and the weak force finally separated. The Higgs field, that invisible ocean permeating all of space, began to give particles their mass. Like walking through water, particles moving through the Higgs field, gaining the property we call weight. Without this field, you would be massless, moving at the speed of light, unable to form, unable to exist as you are now. In the quark epoch, quarks swam freely in a plasma so hot they couldn't bind together. Imagine an ocean of fundamental particles, each one vibrating, existing for only a moment before being created again, annihilated again in the seething heat. This was when matter and antimatter met in equal numbers, and for reasons we still don't fully understand, matter won, just slightly. For every billion antimatter particles, there were 1,000,000,001 matter particles. This tiny asymmetry, this baryogenesis, is why you exist, why anything exists to form atoms at all. Let your jaw release, soften as we drift deeper. The Hadron epoch came next, as the universe cooled enough for quarks to bind, forming protons and neutrons, the building blocks of atomic nuclei, emerging from the chaos. In those first seconds, the universe was like the core of a star, a vast nuclear reactor forging the simplest elements: hydrogen, helium, tiny traces of lithium and beryllium. This primordial nucleosynthesis created the raw materials that would one day become stars, planets, you, your shoulders, melting down into the bed. Then the lepton epoch, when electrons and their heavier cousins dominated the cosmic dance. Neutrinos, those ghost particles, decoupled from everything else, streaming through the universe, even now, even through you, billions passing through your body, every second, never touching, never interacting. A cosmic neutrino background, invisible, untouchable, older than star, like older than atoms. Imagine them drifting through your hands right now as you sink deeper into sleep. For 380,000 years, the universe remained opaque, a fog of plasma, electrons and photons locked in an endless dance. Light couldn't travel, couldn't escape. The universe, dark, despite being filled with light. Then, slowly, as space expanded, as temperature dropped, electrons and protons found each other, combined into the first atoms. This recombination era, when matter became neutral. You're breathing slower now, slower, letting each breath carry you down, and light was free. For the first time, photons could travel unimpeded through space. This moment, this decoupling, created something beautiful, something we can still see today. The cosmic microwave background radiation, the oldest light in the universe, stretched and cooled by 13.8 billion years of expansion. A baby picture of the cosmos when it was just 380,000 years old, showing tiny ripples, tiny temperature variations of 1 part in 100,000. These ripples, seeds of everything, galaxies, clusters. You feel the weight of your arms, heavy against the sheets. Astronomers discovered this ancient light by accident, a persistent hiss in their radio antenna that wouldn't go away. The echo of creation itself, humming, always humming, at a temperature of 2.7 Kelvin, just above absolute zero. If you could see microwave radiation, the entire sky would glow softly, uniformly, with only the faintest patterns, swirls in the light from the last scattering surface, the edge of the visible universe. Thump, thump, your heart finding its quietest rhythm. But those tiny ripples in the cosmic microwave background shouldn't exist. The universe shouldn't be so smooth, so uniform. Light from opposite sides of the universe would never have had time to mix, to reach thermal equilibrium. This is the horizon problem. Regions too far apart to ever have communicated somehow have the same temperature, the same properties. How? Your mind drifting, questioning softly as we float through the dark. The answer: inflation. In the first tiny fraction of a second, between 10 to the minus 36 and 10 to the minus 32 seconds, the universe expanded exponentially, doubling, doubling again, at least 60 times in an instant. This inflationary epoch stretched space faster than light itself, taking a region small enough to be in contact and blowing it up to encompass everything we can see. This solves the horizon problem, explains the flatness problem, why the universe appears geometrically flat when it could have been curved in any direction. Your body expanding, relaxing, every cell releasing. Inflation also explains why we don't see magnetic monopoles, hypothetical particles predicted by grand unified theories that should be everywhere, but aren't. Inflation diluted them, spread them so thin we may never find one, and it explains the density parameter, omega, how the universe sits right on the knife edge between expanding forever and collapsing back. The total density of the universe divided by the critical density equals almost exactly 1, a universe balanced on the edge of possibility. Let your thoughts drift away like clouds, dispersing. After recombination, after light was free, the universe entered the dark ages. No stars yet, no galaxies, just vast clouds of neutral hydrogen, drifting, cooling, gathering under the gentle pull of gravity. For hundreds of millions of years, darkness, true darkness, the universe, waiting, gathering its strength. Your eyelids, so heavy now, barely up, or already closed. It's hard to tell. Then, in that darkness, the first light, population 3 stars, massive, short-lived, made only of hydrogen and helium, no heavier elements yet. These first stars burned hot, burned blue, and died quickly in spectacular supernovae, forging in their final moments carbon, oxygen, nitrogen, silicon, iron. All the elements, heavier than helium, are made in stars. Stellar nucleosynthesis, the alchemy of fusion. You're made of stardust isn't just poetry. Every atom in your body, except hydrogen, was forged in the heart of a star or in the shockwave of its death. Feel yourself made of stars, ancient, drifting. These first stars also released ultraviolet radiation intense enough to ionize the hydrogen around them, turning it back into plasma. This reionization epoch, around 150 million to 1 billion years after the Big Bang, lit up the universe again, created bubbles of ionized gas, expanding, merging, until the entire universe was ionized once more, but this time transparent. Light could travel, stars could shine, visible across the cosmos. Your breathing, almost imperceptible now, gentle, like starlight. Gravity, patient, persistent, pulled matter together. First stars, then clusters of stars, then galaxies. The first galaxies, small, irregular, merging, colliding, growing, galactic cannibalism, larger galaxies consuming smaller ones. This is how galaxies evolve, how they grow. Our own Milky Way has consumed dozens of smaller galaxies, their stars now orbiting in long streams, fossil remnants of ancient collisions. Let your muscles release completely, no tension anywhere. Galaxies themselves cluster, drawn together by gravity. Our Milky Way belongs to the local group, about 50 galaxies, bound together. Our nearest large neighbor, Andromeda, is approaching us at 110 kilometers per second. In about 4 billion years, will collide, merge into one vast elliptical galaxy. But don't worry, space between stars is so vast, no stars will actually hit. They'll pass by each other, like ghosts, rearranging into new orbits, a new shape under new stars. The local group is part of something larger, the Virgo supercluster. Thousands of galaxies, spanning 110 million light years, and that is part of something even larger, Laniakea, Hawaiian for immeasurable heaven, our home supercluster, containing 100,000 galaxies, all flowing, falling, toward a gravitational anomaly we can't quite see, the great attractor, a region of space, pulling everything within hundreds of millions of light years toward itself. Perhaps it's a massive cluster of galaxies, hidden behind the plane of the Milky Way, where dust obscures our view. Perhaps it's something else, something we don't understand. Yet, your body falling softly into gravity's embrace. When we look at the large-scale structure of the universe, we see something beautiful, something unexpected. Galaxies aren't distributed randomly. They form a cosmic web, long filaments of galaxies, strung between massive clusters, separated by vast voids, nearly empty regions containing almost nothing. The Berta's void, 330 million light years across, nearly empty, an absence so vast it's become famous. The universe looks like foam, like soap bubbles, with galaxies on the surfaces and darkness within. Imagine floating through a void, nothing in any direction, just darkness and silence for millions of light years. This structure emerged from those tiny ripples in the cosmic microwave background. Regions slightly denser collapsed faster, forming filaments and clusters. Regions slightly less dense became voids, evacuated as matter fell into the denser regions. Baryon acoustic oscillations, sound waves in the early universe, left an imprint, a preferred scale of 490 million light years, a cosmic ruler allowing us to measure the expansion history of the universe. Your consciousness rippling, oscillating between wake and sleep. Edwin Hubble discovered in 1929 that galaxies are moving away from us. The farther away they are, the faster they recede. This is Hubble's law. Velocity equals the Hubble constant times distance. Not because we're special, not because we're at the center, but because space itself is expanding. Imagine dots on a balloon as you inflate it. Every dot moves away from every other dot. None is the center. The expansion is everywhere, all at once. Let yourself expand, soften into the vastness. The Hubble constant, how fast the universe is expanding, has become controversial when we measure it using the cosmic microwave background and the Friedmann equations describing how the universe evolves. We get one value: 67 kilometers per second per megaparsec. When we measure it using nearby supernovae and Cepheid variables, pulsating stars whose brightness tells us their distance, we get another value, 73. This is the Hubble tension, the crisis in cosmology. These two methods shouldn't disagree, but they do. Perhaps we're missing something about dark energy, about the expansion. Perhaps our model is incomplete. Thump, thump, your heart, unconcerned with cosmic tensions. The Friedmann equations, derived from Einstein's general relativity, tell us how the scale factor, how the size of the universe changes over time. They depend on the density of matter, the density of radiation, the density of dark energy, and the curvature of space. These equations predict the fate of the universe. Will it expand forever or collapse back into a big crunch? Everything depends on the balance of these cosmic ingredients. Your thoughts balancing on the edge of dreams. General relativity tells us that matter curves space-time. Mass and energy bend the fabric of space, and objects follow the curves. That's what we call gravity. Not a force pulling us, but space-time pushing geodesics, the straightest possible paths. Through curved space near massive objects, time itself slows down. This is time dilation. Clock near a black hole runs slower than one far away. Time is not absolute, but relative, flowing at different rates, depending on where you are in the gravitational field. Feel time stretching, slowing as you sink deeper. Black holes, where space-time curves Infinitely, the Schwarzschild radius, the point of no return, where escape velocity equals the speed of light. For Earth, that radius would be 9 millimeters. For the Sun, 3 kilometers. Compress any mass inside its Schwarzschild radius, and you create a black hole, an event horizon, a one-way membrane. Information can go in, but nothing, not even light, can come out. Your awareness drifting toward that horizon between waking and sleep. Yet Stephen Hawking discovered something strange. Black holes aren't completely black. Quantum fluctuations near the event horizon can create pairs of particles. One falls in, one escapes. This Hawking radiation means black holes slowly evaporate over impossibly long timescales, 10 to the power of 67 years for a solar mass black hole. They fade, shrink, and in a final flash, disappear. Even the most massive black holes, even the supermassive ones at the centers of galaxies, billions of times more massive than the Sun, will eventually evaporate into quantum static. Your existence, temporary but beautiful. Supermassive black holes lurk at the centers of most galaxies, including our own. Sagittarius A star, 4 million solar masses. Right now, as you rest, it's pulling stars into wild orbits, some completing a circuit in just 20 years. We've watched them loop around the invisible monster, proving something dark and massive sits at the galactic core, your mind orbiting around the pull of sleep. When black holes feed, consuming gas and stars, they become quasars, the brightest objects in the universe, active galactic nuclei, blasting jets of particles and radiation across millions of light years. Some quasars point directly at us. These blazers flicker and vary on timescales of hours as the jet wobbles slightly, as sweeping across Earth like a lighthouse beam. Let your thoughts be consumed by the dark, peaceful, quiet. Gravitational lensing occurs when light from a distant galaxy passes near a massive object, a cluster of galaxies. The light bends, following the curves of space-time, creating multiple images, arcs, even Einstein rings, perfect circles of light when alignment is perfect. This isn't just beautiful, it's useful. The amount of bending tells us the mass of the lens, including mass we can't see, dark matter, your perception, bending, warping in this space between thoughts. Dark matter makes up 85% of all matter in the universe. We can't see it, can't touch it. It doesn't interact with light at all, but we know it's there from its gravity. Galaxies rotate too fast as to be held together by visible matter alone. They should fly apart, but they don't. Dark matter halos, invisible cocoons, surround every galaxy, providing the extra gravity needed to hold them together. Invisible forces holding you as you drift. What is dark matter? Perhaps WIMPs, weakly interacting massive particles. Perhaps axions, tiny hypothetical particles produced in the early universe. Perhaps primordial black holes, formed in the first fraction of a second after the Big Bang. Or machos, massive compact halo objects, brown dwarfs, or cold white dwarfs, too dim to see. We're still searching, deep underground, in detectors waiting for dark matter particles to bump into normal matter just once. Your body, resting, waiting, in the dark. But dark matter is not the strangest thing. Dark energy is stranger still, making up 68% of everything. It's not in galaxies or clusters, it's in space itself, a property of the vacuum, perhaps the cosmological constant, lambda, Einstein's famous biggest blunder that he later abandoned. But it seems he was right, after all. Empty space has energy, and that energy causes the expansion to accelerate. Feel the space around you expanding gently. In 1998, astronomers studying Type A supernovae, standard candles, exploding white dwarf stars whose peak brightness, we know precisely, discovered something shocking. The universe isn't just expanding, it's accelerating. Galaxies farther away are receding faster than Hubble's law predicts. Something is pushing space apart, faster and faster. This dark energy, this mysterious force, dominates the universe and determines its fate. You're breathing, expanding, accelerating softly into sleep. If dark energy remains constant, if its density never changes, even as space expands, then the universe faces heat death, the big freeze. In this scenario, expansion continues, forever, accelerating. Galaxies move away, faster and faster, eventually receding, faster than light itself, not because they're moving through space, but because space between them is expanding. Eventually, we'll only see our local group, everything else, beyond our cosmic horizon, forever. Your awareness, expanding, dissolving into darkness, star formation, will slow, then stop. In 10 trillion years, when all the gas has been consumed, no new stars will be born. Existing stars will die, one by one. The universe, growing darker, colder, red dwarfs. The smallest stars will be the last to shine, burning for trillions of years, outlasting everything. But even they will eventually exhaust their fuel, fade into cold black dwarfs. Thump, thump, your heartbeat echoing in the emptiness. In 10 to the power of 30 years, protons might decay, matter itself dissolving into lighter particles, atoms no longer stable, everything unraveling. In 10 to the power of 40 years, black holes dominate, the universe slowly evaporating through Hawking radiation, radiating away their mass, atom by atom, quantum fluctuation by quantum fluctuation, until nothing remains but a thin soup of photons and leptons spreading, cooling, approaching absolute zero. let go into the absolute stillness. But this assumes dark energy stays constant. If instead, dark energy grows stronger, if its density increases, we face something more violent, the Big Rip. In this scenario, the accelerating expansion eventually overcomes all forces. First, galaxy clusters are torn apart, then galaxies, then solar systems, then planets. About 3 months before the end, Earth is ripped from the sun. In the final moments, atoms themselves are shredded, electrons torn from nuclei split into individual protons and neutrons, then quarks, space, expanding so fast nothing can hold together, everything dissolving into quantum foam. Your body held together, safe for now as you rest. Or perhaps, if dark energy weakens, if it reverses, the universe could recollapse, the big crunch, expansion slowing, stopping, reversing, galaxies turning blue shifted, approaching rather than receding, temperature rising as space contracts, until everything falls back together into a singularity, perhaps to bounce into a new Big Bang, the Big Bounce, cyclic cosmology, where universes are born, live, die, and are reborn forever, each cycle erasing almost all information from the previous one, an eternal return, cycles of breath, in and out, eternal. Conformal cyclic cosmology, proposed by Roger Penrose, suggests the far future of one universe with only photons traveling at light speed is mathematically identical to the Big Bang of the next. Time loses meaning when nothing has mass, when everything moves at light speed. Eons can pass in an instant. The heat death of our universe becomes the birth of another, an infinite sequence of aeons, each containing the entire lifespan of a universe, stretching forever, time dissolving in the space between heartbeats. The shape of space itself is one of cosmology's questions. Is the universe flat, like an infinite plane, or curved, like the surface of a sphere, or saddle-shaped, with negative curvature? Measurements of the cosmic microwave background suggest flatness. The angles of triangles add up to 180 degrees, parallel lines to never meet, never diverge. Space extends infinitely in all directions. But our measurements have uncertainty. We can only say the universe is very close to flat within our ability to measure. Your body, flat against the bed, perfectly supported. The holographic principle suggests that everything in a volume of space can be encoded on its boundary, like a hologram, where a two-dimensional surface contains all the information to reconstruct a three-dimensional image. Perhaps our universe is a hologram projected from information on a distant boundary. All of reality, everything you've ever experienced, encoded on a two-dimensional surface at the edge of the cosmos. Your dreams, projections of something deeper, unknowable, quantum fluctuations Tiny random variations in the energy of empty space existed even before inflation, even before the Big Bang. The uncertainty principle says virtual particles constantly pop in and out of existence, borrowing energy from the vacuum for the briefest instant. Inflation stretched these quantum fluctuations to cosmic scales, those tiny ripples to become the seeds of galaxies. You exist because of quantum uncertainty, because nothing can ever be perfectly smooth, perfectly still. Let uncertainty carry you into sleep's randomness. String theory proposes that fundamental particles aren't points, but tiny vibrating strings. Different vibrations produce different particles, like notes on a violin string. The mathematics requires 10 or 11 dimensions, most curled up, so small we can't see them, and string theory predicts a vast landscape of possible universes, 10 to the power of 500, different vacuum states, different laws of physics, different values for fundamental constants. Most would be lifeless, unable to form atoms or stars. Your consciousness vibrating at the frequency of sleep. This leads to the multiverse hypothesis. Perhaps all possible universes exist somewhere in eternal inflation. Different regions of space stop inflating at different times, creating bubble universes, each with different physics, or in quantum mechanics, the many worlds interpretation. Every quantum event splits reality into branches, one branch for each possible outcome, an infinite tree of universes constantly branching. You existing in countless variations across the multiverse, making every possible choice in some reality somewhere, infinite versions of this moment, you drifting in all of them. Brain cosmology proposes that our universe is a three-dimensional brain, a membrane floating in higher dimensional space. The bulk. Other brains might float nearby, colliding occasionally, each collision producing a big bang. Gravity might leak between brains, explaining why it's so much weaker than other forces. Our entire universe, just a thin film, vibrating in a space. We cannot perceive vibrations in the membrane of your being. The anthropic principle observes that the universe must be compatible with life for us to observe it. Weak anthropic principle says we see what we see because if it were different, we wouldn't be here. Strong anthropic principle suggests the universe must produce observers, somehow inevitable. But why should it be? Why are fundamental constants fine-tuned to allow chemistry, stars, planets, life, change the strength of gravity by 1 part in 10 to the 34, and stars couldn't form, change the nuclear forces slightly, and carbon couldn't exist? We live in a Goldilocks universe where everything is just right. Just right. This bed, this darkness, this moment, perfect for rest. The Copernican principle reminds us we are not special, not at the center, not privileged observers. Earth is an ordinary planet around an ordinary star in an ordinary galaxy in an ordinary cluster. The universe doesn't care about us. Yet here we are, observing, wondering, briefly conscious in the vast dark. You, small, temporary, or beautifully insignificant. Olber's paradox asks why, if the universe is infinite, eternal, and filled with stars, the night sky is dark. Every line of sight should eventually hit a star. The sky should be bright as the sun's surface. The answer lies in expansion and finite age. Distant starlight is redshifted into invisibility, and the universe hasn't been around forever. Light from the most distant stars hasn't reached us yet. The darkness is evidence of the Big Bang, of a beginning in time. Darkness, wrapping around you, evidence of cosmic truth. Redshift occurs when light is stretched by expansion, moving toward longer wavelengths. Red end of the spectrum. Distant galaxies shift toward red. The farther away, the greater the redshift. We can measure how fast space expanded at different times by looking at different distances. Looking out in space is looking back in time. Light, taking billions of years to reach us, shows the universe as it was, when younger, smaller, denser, looking inward into memory, into dream, seeing your past, your younger self. Blue shift is the opposite. Light compressed, shifted toward shorter wavelength. It happens when objects approach. Andromeda is blue shifted, falling toward us. In our local group, gravity overcomes, expansion, galaxies bound together, but beyond, everything recedes, everything redshifts, the universe expanding, while some structures resist, temporarily holding together against the tide. Your thoughts shifting between colors, between states, sleep approaching. The cosmic distance ladder is how we measure vast distances. Each rung calibrates the next. First, parallax. Nearby stars shift against background as Earth orbits. Then Cepheid variables, pulsating stars whose period relates to luminosity. We know their true brightness, so apparent brightness tells us distance. Then Typeia supernovae's white dwarfs that explode when they reach the Chandrasekhar limit, 1.4 solar masses. These explosions have consistent peak brightness, visible across billions of light years, standard candles lighting the way into deep space, each step taking you deeper into rest, into the cosmic dark. The vacuum of space isn't truly empty. Quantum fields permeate everything, even where there seems to be nothing. Virtual particles appearing and disappearing, borrowing energy from uncertainty. The vacuum seethes with possibility, with potential, never truly still, never truly empty, just like your mind, even in sleep, never quite silent. Dreams rising like particles from the quantum foam, of unconsciousness. Your breathing is shallow now, barely noticeable, like the vacuum, almost nothing, but not quite. Time dilation near massive objects means time flows differently depending on where you are in the universe. A clock on a neutron star runs slower than one in deep space. Your lifetime stretched or compressed by gravity's touch. If you could orbit a black hole close to the event horizon and return, centuries could pass on Earth while you aged only years. Time is not the constant we imagine, but flexible, bendable, relative. Your sense of time bending now, minutes feeling like hours or seconds, impossible to tell. The arrow of time might not be fundamental. The laws of physics work equally well, forwards or backwards. A movie of particles colliding looks the same, reversed. Yet we experience time flowing one direction only. Perhaps this is because of entropy, because the universe began in low entropy, high order. Everything since has been spreading out, becoming more disordered, more random, and our consciousness, our memory, flows along with entropy's increase. We remember the past, the lower entropy state, but not the future. We are entropy detectors, biological arrows pointing toward heat, death. Your consciousness flowing downstream with time, with entropy, towards sleep's disorder. Penrose and Hawking proved that singularities are inevitable in general relativity. Under certain conditions, collapse must continue to infinite density. Black holes must have singularities at their centers. The Big Bang was a singularity in time, where the equations break down, produce infinities. These singularities tell us our theories are incomplete, that something new, quantum gravity perhaps, must take over at the smallest scales, the highest energies, something we haven't discovered yet. At the center of things, unknowns, mysteries. But you don't need to solve them. Just rest. Loop quantum gravity is one attempt to merge quantum mechanics and general relativity. It suggests space-time is not continuous, but discrete, made of tiny loops at the Planck scale. Space itself, woven from these loops, like fabric from threads. At this scale, 10 to the power of minus 35 meters, space becomes granular, pixelated, no smooth continuum, but a quantum foam of geometric structure. If this is true, then singularities don't exist. Density has a maximum. Space cannot shrink infinitely. Thump, thump, your heart, beating in discrete moments, not continuous, but close enough. String theory requires extra dimensions, 6 or 7, curled up small into Calabi-Yau manifolds, complex geometric shapes at every point in space. We move through only 3 dimensions because the others are compactified, rolled up, smaller than we can detect. Different ways of curling up these dimensions produce different physics, different particle masses at different forces. The landscape of string theory is vast, perhaps 10 to the 500 different possible universes, most sterile, lifeless, a few capable of stars and chemistry, and you, curled up like your body in bed, compact, small, conserving warmth. The holographic principle emerged from studying black holes. The entropy of a black hole depends on its surface area, not its volume. All the information about what fell in is somehow encoded on the event horizon. This suggests that three-dimensional space might be a hologram projected from information on a two-dimensional boundary. Everything you experience, every depth, every dimension might be an illusion, a projection from a distant surface at the edge of the universe. Your inner world, three-dimensional and rich, projected somehow from neural surfaces, thin layers, creating depth. The black hole information paradox troubled physicists for decades. If black holes evaporate completely through Hawking radiation, and if that radiation is purely thermal, random, then information that fell in is lost, destroyed, violating quantum mechanics, which says information is conserved. The paradox seems resolved now. Information is preserved in subtle correlations in the Hawking radiation, encoded in ways too complex for us to read. The universe keeps its accounts balanced. What you forget when you sleep is not lost, just encoded in patterns you can't access. In the moment, Hawking radiation arises from quantum effects near the event horizon. One particle of a virtual pair falls into the black hole, the other escapes. To distant observers, this appears as radiation. The black hole loses mass very slowly. A solar mass black hole takes 10 to the 67 years to evaporate. Supermassive black holes, like those at galactic centers, take even longer, 10 to the 98 years or more. The universe will be dark and cold long before the last black hole disappears. Slow evaporation, like consciousness, fading into sleep imperceptibly, molecule by molecule. In the final stages of evaporation, a black hole shrinks rapidly, its temperature rising as it gets smaller. In the last second, it radiates more energy than during its entire previous existence, exploding in a final flash of gamma rays. Then nothing. The singularity gone. The event horizon gone. Just empty space and radiation spreading into the void. A final flash before darkness, like the last thought before sleep takes you. Primordial black holes might have formed in the first second after the Big Bang. When density fluctuations were large enough, regions could collapse directly into black holes without ever being stars. These could be very small or very large. Some might still exist, wandering through space. If they're small enough, they've evaporated by now. If they're larger, they could still be out there, perhaps contributing to dark matter, invisible but present through gravity alone, wandering through the darkness of space, of sleep, invisible presences. The Stohar theorem states that black holes have only three properties: mass, charge, and angular momentum. Everything else about what fell in every detail is lost. All black holes with the same mass, charge, and spin are identical. They have no hair, no distinguishing features. This simplicity is beautiful, elegant, but also troubling, because it seems to destroy information in sleep. You lose distinguishing features too: personality, memory, identity, temporarily erased. Everyone asleep looks similar, breathing, unconscious, simple. Rotating black holes, described by the Kerr metric, are more complex than non-rotating ones. They have two event horizons. The outer is the point of no return. The inner surrounds the ring singularity. Between them, the ergosphere, where spacetime itself is dragged around, rotating with the black hole. You can enter the ergosphere and escape, unlike the event horizon, but you cannot stay still. Space itself is moving, carrying you around and around, spinning, your thoughts carried around by forces you don't control as sleep pulls you in. The Penrose process extracts energy from rotating black holes. Objects entering the ergosphere can split. One part falls into the black hole, the other escapes with more energy than it started with. The black hole's rotation slows slightly, its energy transferred. This might power quasars, blazars, active galactic nuclei, black holes feeding on matter, spinning rapidly, throwing off jets of particles and energy, visible across billions of light years. Energy extracted from rest. Paradoxically, you must sleep to be energized. When you wake, quasi-stars are hypothetical objects from the early universe. A black hole surrounded by a massive envelope of gas. The black hole accretes matter, releasing energy that keeps the envelope from collapsing. These could grow to thousands of solar masses, seeds for supermassive black holes that we see in distant galaxies when the universe was young. How supermassive black holes grew so large so quickly remains mysterious. Quasi-stars are one possibility. Mysterious origins, like sleep itself, why we need it, how it restores us, still not fully understood. The M87 galaxy, at the center of the Virgo cluster, has a supermassive black hole, 6.5 billion times the Sun's mass. In 2019, the Event Horizon Telescope took its picture, a ring of light surrounding darkness, the photon sphere where light orbits, the black hole before falling in or escaping, the shadow, the silhouette of the event horizon against the glowing accretion disk, a real image of a black hole. something Einstein thought we'd never see, seeing the invisible like catching the moment you fall asleep, usually impossible, but sometimes glimpsed. Our own galaxy's black hole, Sagittarius A star, is smaller, 4 million solar masses. We've watched stars orbit around it. S2, the brightest, completes its orbit in 16 years. At closest approach, it reaches 7% the speed of light, experiencing time dilation, gravitational redshift, all the strange effects of general relativity. These stars are laboratories testing Einstein's theory, and it holds perfectly. Every prediction confirmed, orbiting around the center of your own galaxy, your own being, the central mystery of consciousness. The galaxy rotation problem was the first hint of dark matter. Vera Rubin measured how stars move in galaxies. They should move slower at the edges, like planets in the solar system, but they don't. Stars at the edge move just as fast as stars near the center, as if the galaxy is embedded in a larger halo of invisible mass. This dark matter halo extends far beyond the visible stars, 10 times larger, 10 times more massive, holding galaxies together with invisible hands, invisible support, holding you together as you sleep, muscles relaxed, but something keeps your form. The bullet cluster provides direct evidence for dark matter. 2 galaxy clusters collided. The visible matter, hot gas, interacted and slowed down, shown by X-rays, but the dark matter passed through, shown by gravitational lensing. The mass is separated from the light. Dark matter, revealed by its gravitational influence, bending light from galaxies behind. This image is one of the strongest proofs that dark matter is real and separate from normal matter. Collision in slow motion, like thoughts colliding as you drift, dreams beginning to form, WIMPs, weakly interacting massive particles, are the most popular dark matter candidate. They'd interact only through gravity and the weak nuclear force, making them nearly impossible to detect. Deep underground, in mines and tunnels, detectors wait, shielded from cosmic rays, waiting for a WIMP to bump into an atomic nucleus just once, but so far, nothing. The darkness keeps its secrets, waiting in stillness, in silence, for something that might never come, like waiting for sleep on difficult nights. Axions are another candidate. Extremely light particles propose to solve the strong CP problem in quantum chromodynamics. If they exist, they'd be produced in abundance in stars and in the early universe. A sea of axions might pervade the galaxy, passing through you constantly. Experiments search for them by looking for their conversion into photons in strong magnetic fields, a faint signal, a whisper in the electromagnetic spectrum. Whispers in the dark, almost inaudible, like this voice, fading as you sink deeper. The cosmic microwave background has been mapped with exquisite precision by satellites, COBE, BIASMAP, Planck, each one revealing more detail, more structure in the temperature fluctuations, hot spots and cold spots, patterns that tell us about the density of matter, the density of dark energy, the geometry of space. From this map, we've learned the universe is flat. Within measurement error, the angles of triangles sum to 180 degrees, exactly flat, like your body pressed against the bed, geometry of rest. The power spectrum of the cosmic microwave background shows peaks at certain angular scales. These acoustic peaks result from sound waves in the primordial plasma before recombination, compression and rarefaction, frozen in place when atoms formed. The position of these peaks tells us the ratio of baryonic matter to dark energy. With incredible precision, we know the universe is 68% dark energy, 27% dark matter, 5% ordinary matter. Everything we see, everything we are, is just 5%. 5% or less of you is actually awake right now. The rest already sleeping. Baryonic acoustic oscillations are the same physics imprinted on galaxy distributions. Today, the sound waves from the early universe set a preferred scale, about 490 million light years, for how galaxies cluster. We see this scale in galaxy surveys, a cosmic ruler stretching across the sky, allowing us to measure the expansion history independent of other methods, all telling the same story. Dark energy is real and accelerating. Expansion, oscillations in your breathing, regular, rhythmic, marking time as you drift. The Laniakea supercluster, meaning immeasurable heaven in Hawaiian, is our home on the largest scales. It contains 100,000 galaxies, including the Milky Way, the Local Group, the Virgo cluster, all flowing like rivers toward the supercluster's center, defined not by proximity, but by motion, by shared velocity, all moving together as one structure, bound by gravity in the expanding universe. Moving together, your body and the bed and the room, all part of one system, one moment of rest. The great attractor lies in the direction of the constellation Centaurus, a gravitational anomaly pulling our local group and thousands of other galaxies toward itself at 600 kilometers per second. We're falling towards something we can't quite see, hidden behind the zone of avoidance where the Milky Way's disk blocks our view. Perhaps it's the Norma cluster, perhaps something else, a concentration of mass that will eventually, in millions of years, join, falling, pulled by invisible forces like gravity's pull into sleep, irresistible. Beyond the great attractor is an even larger structure, the Shapley supercluster, the most massive concentration of galaxy in the nearby universe, pulling not just us, but the great attractor itself, everything falling toward even greater concentrations of mass, the universe flowing in vast currents on scales. We're only beginning to map currents pulling you deeper into rest, into the vast ocean of sleep. The cosmological principle states that on large scales, the universe is homogeneous and isotropic, the same in all directions. No special locations, no center, no edge, just uniform. Observations confirm this. Galaxy distributions become smooth. Beyond a few 100 million light years, the cosmic microwave background is uniform to 1 part in 100,000. We live in a democracy of space, every location equally valid, equally ordinary, no special position needed to sleep. Just lie down anywhere and rest comes. But some structures challenge this. The Hercules Corona Borealis Great Wall, a filament of galaxies 10 billion light-years long, one of the largest structures ever found, possibly too large to form in the age of the universe, given our models, a statistical fluke or a hint that something in our understanding is incomplete. The universe keeps presenting puzzles, anomalies, things that don't quite fit. Not everything needs to fit to make sense. Contradictions can coexist in dreams, in the space between thoughts. Quasars were discovered in the 1960s, star-like objects with enormous redshifts, impossibly distant, yet incredibly bright, outshining entire galaxies, the brightest objects in the universe, powered by supermassive black holes, accreting matter, converting mass to energy with 10% efficiency, far better than fusion, which manages less than 1%. The accretion disk around the black hole heats to millions of degrees, glowing across all wavelengths. Brightness from darkness, light from the deepest void, like consciousness from the sleeping brain. Some quasars vary in brightness over hours or days. This tells us the emission region must be small, light hours across, smaller than our solar system, yet outputting the energy of 1 trillion suns, all from matter, spiraling into a black hole, no larger than our planetary system. The universe concentrating power in the smallest spaces, paradoxically, the largest effects from the smallest engines. Your brain, small yet containing all your memories, all your thoughts, all your dreams, vast worlds in tiny spaces, blazars are quasars whose jets point directly at us. The jet, a stream of particles accelerated to nearly light speed by magnetic fields, twisted and wound in the accretion disk, shooting out along the black hole's rotation axis across thousands or millions of light years. When we look straight down the barrel of this cosmic gun, we see a blazer, intensely bright, rapidly variable, as the jet wobbles slightly, sweeping its beam across Earth like a lighthouse. Direct line between you and sleep. No obstacles, just sink straight down. Active galactic nuclei come in many types: Seyfert galaxies, radio galaxies, quasars, blazars, all the same phenomenon, seen from different angles, unified by accretion onto supermassive black holes. About 10% of galaxies are active. The rest, including our own, have black holes that are dormant, starving, not currently feeding. In the past, the Milky Way's black hole was active. It will be active again when we collide with Andromeda. New gas funneled to the center, reigniting the engine, dormant like you, at rest, not active, conserving energy for when you'll need it later. Galaxy mergers trigger star formation. The collision compresses gas clouds, causing them to collapse and form stars in bursts. Starburst galaxies form hundreds of solar masses in stars per year. Our Milky Way forms only one or two. In mergers, efficiency increases briefly until the gas is exhausted or blown away by supernovae and stellar winds. Then star formation stops. The merged galaxy becomes an elliptical, red and dead, no gas, no young stars, just old stars, you slowly aging, slowly dying. Bursts of activity and followed by quiet, like waking life and sleep. Alternating, cycling, elliptical galaxies are smooth, featureless. No spiral arms, no disks, just ellipsoidal distributions of old stars. They form from mergers of spiral galaxies. The collision scrambles orbits, turning ordered rotation into random motion, velocity dispersion. In 4 billion years, when Andromeda and the Milky Way merge, will form an elliptical galaxy. Milkomeda, red, quiet. No more spirals, no more star formation, just slowly evolving toward the inevitable. Fade, smooth, featureless, like deep sleep, without dreams, just dark, just rest. Globular clusters are ancient, nearly as old as the universe itself, dense balls of hundreds of thousands of stars orbiting galaxies in elliptical paths. Their stars are metal poor, formed before heavier elements were abundant. By studying their color and brightness, we can estimate their age. The oldest are 13 billion years or more, just slightly younger than the universe. These clusters are fossils, witnesses to the earliest epochs of galaxy formation, ancient witnesses to your life, memories deep in your brain, older than you remember, watching everything. Type Ia supernovae occur when white dwarfs reach the Chandrasekhar limit, 1.4 solar masses. At this mass, electron degeneracy pressure can no longer support the star. It collapses, triggering runaway thermonuclear fusion. The entire star explodes. in seconds, releasing energy equal to what the sun will produce in its entire lifetime, briefly outshining its host galaxy. Sudden release, like the moment you finally fall asleep, tension releasing all at once, because all Type Ia supernovae reach the same mass before exploding. They have similar peak brightness, making them standard candles. We can measure their apparent brightness and calculate their distance. Using this method, in 1998, 2 teams measured distant supernova, expecting to find expansion slowing due to gravity. Instead, they found expansion accelerating, dark energy discovered, leading to a Nobel Prize and a revolution in cosmology. Unexpected discoveries, like sudden insights at the edge of sleep, when logic dissolves, truth appears. Cepheid variables pulsate regularly, expanding and contracting. The period relates directly to their intrinsic luminosity. Brighter Cepheids pulsate slower. This period luminosity relation, discovered by Henrietta Leavitt, allows us to measure distances to nearby galaxies where we can see individual Cepheids. They're the second rung on the cosmic distance ladder after parallax, before supernovae. Regular pulsations, like breathing, like heartbeat, marking time, marking distance from wake to sleep. The cosmic distance ladder requires careful calibration. Each rung depends on the previous one. Errors propagate upward. Uncertainty compounds. This is partly why the Hubble tension exists. Different methods give different values for the Hubble constant. Perhaps one rung is slightly wrong, introducing systematic error, or perhaps something about the universe we don't understand. New physics hiding in the discrepancy, uncertainty compounding. But it's okay. Not everything needs precision. Sometimes approximation is enough. LIGO, the Laser Interferometer Gravitational Wave Observatory, uses lasers bouncing between mirrors 4 kilometers apart. When a gravitational wave passes through, it stretches space in one direction, compresses it in the perpendicular direction by a tiny amount, 1,000th the diameter of a proton. Yet LIGO measures it, detecting waves from colliding black holes billions of light years away. Sensitivity to the smallest changes, like your body, sensitive to comfort, adjusting position unconsciously as you sleep. The first detection, GW1 914, occurred on September 14th, 2015. 2 black holes, 36 and 29 solar masses, orbiting each other, spiraling inward, accelerating until they merged in a fraction of a second. 3 solar masses converted to energy, purely in gravitational waves, space itself ringing like a bell. After the collision, the chirp increasing in frequency and amplitude until the merger. Then silence, a final black hole 62 solar masses, spinning, settling down, the chirp of existence building to a peak, then silence, like each day, culminating in sleep. Since then, dozens more, mergers detected, black holes of various masses, neutron stars colliding, GW 170817, a neutron star merger detected in gravitational waves and electromagnetic radiation, gamma rays, X-rays, visible light, radio waves, multi-messenger astronomy. Observing the same event through different channels, we learned that neutron star mergers produce heavy elements, gold, platinum, uranium, forged in the incredible pressures of colliding neutron stars. The gold in your jewelry was made in a cosmic collision billions of years ago. Everything coming from collisions, interactions, in sleep, your neurons still firing, still interacting in patterns you don't control, dreams emerging from chaos, thump, 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 your heart still beating as the universe expands around you, as galaxies drift apart, as you drift into deeper and deeper rest. The universe keeps turning and will keep drifting, floating together. Gravitational waves, ripples in space-time itself, were predicted by Einstein, but not detected until 2015. LIGO and Virgo, laser interferometers, measured distortions in space-time 1,000 times smaller than a proton. Two black holes, orbiting, spiraling inward, finally merging, created waves that traveled across the universe for over 1 billion years, arriving at Earth on September 14th, 2015. We felt the space-time ripple of a collision that happened when Earth had only simple life, single cells, not yet complex, ripples from ancient events washing through you now as you rest. Since then, dozens more, mergers detected, black holes, neutron stars colliding, releasing more energy in gravitational waves in a fraction of a second than all the stars in the visible universe combined. These waves carry information about the masses, spins, distances of merging objects, a new way to observe the universe, not through light, but through the fabric of space itself. Your body, sensitive to invisible forces, the pull of sleep, the curvature of rest. Neutron stars, formed when massive stars collapse, crushing protons and electrons into neutrons. A teaspoon of neutron star matter weighs 1 billion tons. Pulsars are neutron stars, spinning rapidly, beaming radiation from magnetic poles. Like cosmic lighthouses, some spin hundreds of times per second, millisecond pulsars, their timing so precise they rival atomic clocks. We use them as natural timekeepers to detect gravitational waves, searching for tiny changes in their rhythm. Thump, thump, your heart, keeping time with the cosmos. Magnetars are neutron stars with magnetic fields 1,000 trillion times Earth's field, strong enough to tear atoms apart from 1,000 kilometers away. When magnetars have starquakes, crust cracking, rearranging, they blast gamma-ray bursts across space, the strongest magnetic fields in the known universe, distorting even the vacuum of space itself. Powerful forces, invisible, holding the universe together. Wormholes or Einstein-Rosen bridges are solutions to Einstein's equations. Tunnels through space-time, connecting distant points, or even different times, but they're unstable, collapsing instantly unless held open by exotic matter with negative energy density, something we've never seen and might be impossible. Traversable wormholes remain science fiction, but the mathematics allows them, the universe permitting what we dare to imagine. Tunnels in your mind, connecting thought to dream, unstable, collapsing into sleep. The arrow of time points from past to future. Entropy, the measure of disorder, always increases. This is the second law of thermodynamics. Ice melts, heat spreads, disorder grows. You can't unscramble an egg. But why? The laws of physics work the same, backward and forward, yet we experience time flowing in one direction, perhaps because the Big Bang was a low entropy state, highly ordered. Everything since has been sliding toward equilibrium, heat death, maximum entropy, when nothing can change anymore. Your body relaxing into entropy, disorder, release, sleep's formlessness. The information paradox asks what happens to information that falls into a black hole. According to quantum mechanics, information cannot be destroyed, but black holes evaporate completely. Where does the information go? Perhaps it's encoded in the Hawking radiation, in subtle correlations, too complex to read. Perhaps it's preserved on the event horizon, in a hologram. Perhaps something deeper about quantum mechanics and gravity remains undiscovered. Questions dissolving as awareness fades. Cosmic strings are hypothetical, one-dimensional defects in space-time, like cracks in ice as water freezes. If they exist, cosmic strings would be incredibly thin, less than a proton across, but incredibly dense and infinitely long, stretching across the universe, moving at nearly the speed of light. If you encountered one, it would slice through anything effortlessly. But we've never detected cosmic strings. They might not exist, or they're too rare, too faint, lost in the vast dark. Threads of possibility weaving through the darkness. Magnetic monopoles are another prediction of grand unified theories. Particles with only north or south magnetic pole, not both. Every magnet we've ever found has two poles. Cut it in half, you get two magnets. each with both poles, but in the early universe, in phase transitions, monopoles should have formed. Where are they? Perhaps diluted by inflation, spread so thin we'll never find one. Perhaps they don't exist. Another mystery in the quantum cosmos, searching for something that might not be there, like grasping at dreams upon waking. The Lyman alpha forest is a pattern in light from distant quasars. As light travels toward us, it passes through clouds of hydrogen. Each cloud absorbs light at a specific wavelength. The Lyman alpha line, redshifted by different amounts depending on distance, creating a forest of absorption lines in the spectrum. These clouds trace the cosmic web, filaments of gas between galaxies, invisible otherwise. The forest tells us about the distribution of matter across billions of years, light filtering through layers of reality, layers of consciousness towards sleep. The Sachs-Wolf effect describes how photons lose energy climbing out of gravitational potential wells. Light from the cosmic microwave background passing through over dense regions gets redshifted, creating cold spots. This imprints the gravitational landscape of the early universe onto the oldest light. The integrated Sachs-Wolf effect occurs when dark energy changes the depth of potential wells over time. Another subtle signature in the cosmic microwave background, another clue to cosmic history. Your energy sinking into potential wells, gravity pulling you towards sleep. The Sunyaev-Zeldovich effect occurs when cosmic microwave background photons pass through hot gas in galaxy clusters. Electrons scatter the photons, shifting them to higher energies, creating shadows. In the microwave sky, this effect allows us to find distant clusters, independent of redshift, weighing the universe, counting clusters at different epochs to understand how structure has grown over time. Shadows deepening around you, embracing you. Cosmic shear is the distortion of galaxy shapes by gravitational lensing from foreground mass, not strong lensing, creating multiple images, but weak lensing, slightly stretching galaxy shapes by a few percent by measuring thousands of galaxies. We can map the dark matter is between us and them, creating three-dimensional maps of dark matter distribution across the universe, seeing the invisible through its subtle touch on light, your shape softening, blurring in the borderlands of sleep. Dark flow is a controversial detection of a preferred direction in the motion of galaxy clusters, as if something beyond our cosmic horizon is pulling everything toward one region, perhaps a massive structure, the unobservable universe, perhaps an artifact of measurement errors. The evidence remains debated, uncertain, like so much in cosmology, where we grasp at signals in noise, flowing drifting in unseen currents, carrying you. The Eridana supervoid, or the CMB cold spot, is a region in the cosmic microwave background that's colder than expected. Perhaps it's just a statistical fluctuation, 1 in 50,000, bound to occur somewhere, or perhaps it's evidence of something stranger, a collision with another universe, or a supervoid so large it shouldn't exist, given our models, an anomaly in the cosmic baby picture, way that we don't quite understand, cold, spreading through your limbs, comfortable, relaxing, heavy. The false vacuum is a terrifying possibility. Perhaps the Higgs field that gives particles mass sits in a metastable state, not the true lowest energy, but a local minimum, like a ball in a bowl on a hillside, stable for now, but not truly stable. A quantum tunneling event could create a bubble of true vacuum, expanding at the speed of light, rewriting the laws of physics as it goes, destroying everything in its path, atoms falling apart as the Higgs field suddenly has a different value. But this is very unlikely. The universe has lasted 13.8 billion years. The false vacuum, if it exists, appears stable enough for cosmological timescales. You're safe to rest, safe to sleep. A spacetime holds its shape around you. Particle horizons define the distance light could have traveled. Since the Big Bang, our observable universe is a sphere 46 billion light-years in radius, not 13.8 billion, because space has been expanding while light traveled. The edge is not a physical boundary, just the limit of what we can see. Beyond it, space continues, perhaps forever, filled with galaxies we'll never observe, never know about, forever beyond. Our cosmic horizon, horizons of consciousness, as you drift towards sleep's boundary. Event horizons are different. They mark points from which no signal sent now will ever reach us. Because of accelerating expansion, galaxies beyond our event horizon recede faster than light. Information from them will never arrive, not ever, no matter how long we wait. The universe forgetting itself, information being lost permanently to expansion, letting go of what cannot be held, releasing into the unknown. Modified Newtonian dynamics, or MOND, proposes that Newton's laws break down at very low accelerations. Instead of dark matter, perhaps gravity simply works differently on galactic scales. MOND successfully predicts galaxy rotation curves without dark matter, but it struggles with clusters with the cosmic microwave background. Most cosmologists favor dark matter, but MOND reminds us that our theories might need revision, that what seems like missing mass could be misunderstood physics. Your understanding releasing its grip, allowing mystery to exist. Dark fluid theory attempts to unify dark matter and dark energy into a single substance with negative pressure. Perhaps there's just one dark component that behaves like matter in dense regions and like energy in empty space. Elegant, if true. Reducing two mysteries as seemed to one, but the evidence just remains inconclusive. The universe keeping its secrets. Fluid darkness surrounding you, supporting you as you float. Entropic gravity, proposed by Eric Verlinde, suggests gravity isn't fundamental but emergent from entropy, from information. Space-time itself might be an illusion, like temperature or pressure, emergent from molecular motion, gravity emerging from deeper quantum information. If true, it would revolutionize our understanding, but it's controversial, uncertain. Most physicists remain skeptical. Emergence from the deep of sleep, pulling you down. Simulation theory in cosmology asks whether our universe might be a simulation run by a more advanced civilization in a higher reality. We'd have no way to tell from inside. The physics would seem real, consistent, because those are the rules programmed in. Some cosmologists take this seriously, calculating probabilities. Others dismiss it as unfalsifiable, beyond science, into philosophy, reality and dream blurring together. Which is which? Does it matter? Penrose diagrams are maps of space-time that compress infinity into finite pictures. They show the entire history of a universe, or a black hole, from Big Bang to heat death, past and future, light cones, horizons, singularities, all visible in one diagram, a bird's eye view of space and time laid out like a map, showing where light can reach, where it cannot, the structure of causality itself, mapping your journey from wake to sleep to dream, all visible from above. The ekpyrotic universe is another alternative to inflation. It proposes our Big Bang was caused by the collision of two brains in higher dimensional space. The collision released energy, creating our universe, and might happen again and again, cycles of creation without a true beginning or end, just collisions bouncing through higher dimensions we cannot see, cycles breathing in and out, sleeping and waking, eternal rhythm. Quantum loop cosmology applies loop quantum gravity to the early universe. It suggests the Big Bang wasn't a singularity, but a bounce from a previous collapsing universe. Quantum effects prevented infinite density, creating a minimum volume. Space cannot shrink below the Planck scale, so the universe rebounds, expands again. The big bounce, emerging from quantum mechanics, bouncing softly between states of being and not being. The Sloan Great Wall is a galactic filament, 1.37 billion light-years long, one of the largest known structures, made of thousands of galaxies strung together in a vast web. It challenges the cosmological principle that the universe should be homogeneous on large scales. The end of greatness is the scale about 370 million light years, beyond which the universe becomes smooth and uniform. But structures like the Great Wall seem to violate this, pushing the boundaries of what we thought possible. Vast structures in the darkness, too large to comprehend. Let them be. Void galaxies exist in the cosmic voids, the empty regions between filaments. These galaxies are unusually isolated, with no neighbors. For millions of light years, they formed in underdense regions, somehow against the odds, living lonely in the darkness between the cosmic web. How did they form? We're still learning, still discovering that even voids aren't completely empty. Isolation in darkness, peaceful, serene, nothing required of you. Dark stars are hypothetical from the early universe. When the first stars formed, they might have been powered not by fusion, but by dark matter, accumulating in their cores, annihilating, releasing energy. These dark stars would be cooler, larger, longer lived than normal stars, eventually us collapsing into black holes, perhaps extinct now, a phase the universe passed through and left behind. Thump, thump, different kinds of fire, different ways to shine. The cosmic ray background consists of high-energy particles, protons mostly, smashing into Earth from all directions, from supernovae, from pulsars, from active galactic nuclei. Some are accelerated to energies so high we don't understand how. The Oh My God particle, detected in 1991, had energy of 320 million trillion electron volts, like a baseball traveling 90 kilometers per hour, concentrated in a single atomic nucleus. Where did it come from? We still don't know. Energy streaming through space, through you, as you rest, oblivious, peaceful. Cosmological perturbation theory studies how tiny variations in the early universe grew into galaxies. It treats perturbations as ripples on a smooth background, using linear approximations. When fluctuations are small and nonlinear simulations, when they grow large and start interacting. This theory connects the quantum fluctuations of inflation to the galaxies. You see at night a mathematical bridge from the smallest scales to the largest, ripples spreading through your awareness, growing, dissolving into sleep. The age of the universe is measured by multiple methods, all converging on about 13.8 billion years from the Hubble constant and the expansion history from the oldest stars in globular clusters, whose ages we can estimate from nuclear physics, from the cosmic microwave background, whose properties depend on age when it formed. All methods agree, within uncertainties, The universe, ancient but not eternal, had a beginning, will have an end. Your own life, a brief flash in cosmic time, here, now, breathing, this moment. Nucleated universe theory suggests universes might nucleate like bubbles in a false vacuum, quantum tunneling, creating true vacuum bubbles that expand, becoming universes, an eternal multiverse constantly bubbling with new universes. Ours, just one bubble among infinite others, each with potentially a different physics, most stillborn, unable to produce anything interesting. A few, like ours, capable of complexity, stars, life, consciousness, wondering, bubbles of thought, forming, popping in the stillness. The last scattering surface is where cosmic microwave background photons last interacted with matter at recombination 380,000 years after the Big Bang. It's a sphere surrounding us, 46 billion light years away now. Due to expansion, every direction we look in the microwave spectrum, we see this surface, the edge of the visible universe. Beyond it, the universe was opaque. Before it, light couldn't travel. This is the farthest we can ever see. With photons, our cosmic horizon painted across the sky, your horizon, between wake and sleep, the edge of awareness, fading. When we measure the universe's parameters, density, curvature, expansion rate, we find ourselves in a remarkable situation, balanced on critical density, almost exactly per biam, flat space-time. The total mass energy within the critical density to a few percent. How unlikely is this? It's the flatness problem. Why should the universe be so precisely balanced unless inflation stretched it to near perfect flatness? A tiny patch blown up so large that curvature becomes undetectable. Balance, perfect as you rest, neither floating nor falling, just being. Quintessence is a proposed form of dark energy that changes over time. Unlike the cosmological constant, which is truly constant, quintessence is a dynamic field rolling slowly down a potential, motivated by particle physics, by string theory. It might explain why dark energy has the value it does. Why now? Or it might be unnecessary complexity. The simplest explanation, the cosmological constant, might be correct. We're still measuring and still testing, watching how expansion accelerates to see if it changes over time. Change or constancy. Either way, the universe expands and you contract into sleep. The Fermi paradox in cosmology asks, where are they? If the universe is billions of years old and contains billions of galaxies, each with billions of stars, many with planets, why haven't we seen any signs of alien civilizations? Perhaps life is rare. Perhaps intelligence is rare. Perhaps civilizations destroy themselves or transcend physical form, or are hiding, or we're too early. The universe recently became conducive to complexity. Perhaps we're among the first, or perhaps we're alone. In all this vastness, just us, temporarily conscious, briefly wandering and before returning as to cosmic dust. Alone or accompanied, it doesn't matter now. In the dark, where you rest, the cosmological constant problem is perhaps the worst prediction. In physics, quantum field theory predicts the vacuum energy should be enormous, 10 to the power of 120 times larger than observed. Yet measurements show dark energy is tiny, positive, but barely there. Why? This is the crisis. Some call it the worst failure of theoretical physics, or perhaps our most profound clue that something deep about quantum mechanics and gravity remains unknown. Vast discrepancies between theory and reality, yet the universe persists, and so do you, breathing, resting. Some cosmologists propose the universe is headed toward vacuum decay, a phase transition where the Higgs field finds a lower energy state. This bubble of true vacuum would expand at light speed, consuming everything, rewriting physics as it goes. Inside the bubble, atoms couldn't exist, electrons might be massless, chemistry impossible, everything we know erased, but calculations suggest this is extraordinarily unlikely, at least for trillions of years, longer than stars will burn. You can rest easy tonight, rest easy, safe in this moment, this eternal now. Cosmology asks the biggest questions. Where did we come from? Where are we going? What is everything made of? And increasingly, we have answers, incomplete, uncertain, but real. We've measured the age of the universe, traced its expansion, mapped its contents. We know it began in a hot, dense state. We know it's expanding, accelerating. We know its fate, at least the most probable outcomes. Questions fading now, answers unimportant as sleep takes over. But the deepest question remains, why? Why does the universe exist at all? Why these laws of physics and not others? Why something rather than nothing? These questions take us beyond science, into philosophy, into the unknowable. Perhaps there's no answer. Perhaps the universe simply is brute fact, requiring no explanation, no purpose, no meaning, except what we briefly create. Or perhaps meaning isn't found, but felt in moments like this, resting, breathing, existing. Enough. Every atom in your body forged in stars, every breath you take contains atoms that were once inside other people, other animals, scattered across the world by wind, by water, by time. We are the universe, experiencing itself. Carl Sagan said, we are stardust, contemplating stars, briefly aware of the vast cosmic story from which we emerged and to which we will returning to the source, to the silence, to the dark, where everything comes from. The expansion of space continues. Right now, as you rest, galaxies receding a few thousand kilometers per second per megaparsec, space itself growing, dark energy pushing, the universe unfolding, indifferent to your dreams or your waking, the cosmos, vast, ancient, temporary, like everything, like you, vast, ancient, temporary, beautiful. This moment, this breath, heavier, heavier, your body sinking into the mattress, into the dark, shoulders releasing, jaw softening, each breath and slower, deeper, matching the pace of cosmic expansion. The universe breathing out for billions of years, one long, slow exhalation into the void, exhaling, releasing, letting go of everything. Everything. If you're still listening, it's okay. Some nights, sleep comes slowly. Let these words wash over you like waves, carrying you gently toward rest. There's nowhere to be, nothing to do. Just be here in the dark, feeling your body, breathing, existing for this moment in the cosmic story. You don't have to understand cosmology. You don't have to remember any of this. Just let it flow through your mind like water, images, concepts, drifting past stars, galaxies, the fabric of space, all of it, distant, dreamlike, unimportant now, compared to the simple fact of your breathing, your heartbeat, your presence, here, now. Thump, thump, thump. The universe doesn't need your attention. It will expand whether you watch or sleep. Dark matter will continue holding galaxies together. Dark energy will continue pushing space apart. Black holes will continue their patient evaporation. All of it happening, whether you know or not. So you can let go, release your curiosity. For now, let consciousness dim like stars, dying, slowly, dimming, fading, almost gone. Perhaps you're dreaming now, this voice, part of your dream, weaving cosmology into strange narratives, galaxies, becoming faces, black holes, becoming feelings, the cosmic web, mapping onto your neural networks, the expansion of space, your awareness broadening, then narrowing as sleep pulls deeper, dream or wake, the boundary dissolving. In the ekpyrotic model, the universe ends and begins in collision, brains touching, creating fire, creating space, creating time. Perhaps you're the collision point where wake and sleep meet, creating the dreams that populate your night. Tiny universes born in your mind, living briefly, dying when you wake, forgotten but real while they lasted. Your universes collapsing, reforming, night after night. The observable universe has a horizon beyond which we cannot see. Your consciousness too has horizons beyond which you cannot reach right now. Parts of yourself beyond the event horizon of awareness, dark, unknown, but there, still there, just out of reach as you drift further into sleep's gravity well, falling into yourself, into the dark, peaceful, silent, somewhere on the cosmic web, on one of those thin filaments, connecting clusters, is a small galaxy with a small star, with a small planet where someone is lying down, breathing just like you under different stars, but experiencing the same human need for rest, for peace, for the letting go that sleep provides. You're not alone in this, even though you'll never meet, never know each other. You share this with countless beings across space and time, connected by the universal need to sleep heavier, your eyelids, your limbs, your thoughts, all of it heavy, sinking, the mattress, becoming, all of space supporting you as dark energy supports the cosmos, unseen but essential, holding everything or in balance, you floating on the fabric of space-time, curving down around your body, everything falling together toward rest. The universe keeps turning, the expansion stretching, the very fabric of space between us, the galaxies drifting apart, the stars slowly dying, entropy increasing, heat spreading thin until only darkness remains. But not yet, not tonight. Tonight, there are still stars, still galaxies, still you, breathing, resting, in the quiet, in the dark, and we'll keep drifting, floating together through the mysteries. 100 cosmology mysteries, looping softly, endlessly, through the night